There are many functions whose limits give some particularly interesting behavior. For example, sine of 1 over x is one of these such functions as x approaches 0. If you recall from the last few videos, we can investigate these limits using a table and by looking at values on the left side of 0 and on the right side of 0. If I look at the function outputs when approaching 0 from the left, I can see that there is clearly no trend. The function outputs just kind of bounce around. We have positive numbers, we have negative numbers, and we're not seeming to approach any particular value. We're not sort of landing on any particular value like we have seen in the past. And of course, if you're not convinced by this, you can use additional values whenever you want. I can get closer and closer to 0. I can use negative 0.00001 and so on and so forth. You can always add more values to these tables. Likewise, as we approach from the right, we can see that there's no trend either. This leads me to the conclusion that the limit as x approaches 0 of sine of 1 over x actually does not exist. That there's no clear trend. We're not clearly approaching any value. It kind of just bounces all over the place. What we call this is uncontrollable oscillation. These values are oscillating between positive and negative numbers, and they're just jumping all over the place, and they're not clearly trending toward any particular value. Piecewise functions can also be a little bit tricky when you're trying to find a limit at that transition point. Notice in this piecewise function, the transition point is 2. On the left-hand side of 2, we are evaluating this function, and on the right-hand side of 2, we are evaluating this function. So if I'm on the right side of 2 for numbers that are greater than or equal to 2, the outputs of my function are going to come from x squared minus 4. And if we are putting in values strictly less than 2, the outputs of our function are going to come from x plus 1. So when we build our left-handed and right-handed tables, we need to keep that in mind. So here's my left-handed table. And here is my right-handed table. Now, like I said, if we're using the left-handed table, if we want our function outputs from the left-hand side of 2, in other words, if we're trying to evaluate the limit as x goes to 2 from the left, we need to use this x plus 1 function for our function outputs. So I'll go ahead and fill that table in for us now so we can see. Now on the left-hand side, as we're approaching x from the left, we can see a clear trend. We can clearly see that we're approaching 3. It's a very clear trend. The outputs of this function as we approach 2 from the left are approaching 3. So that means the limit as x approaches 2 from the left of this piecewise defined function is 3. Now let's investigate the right-hand side outputs. I'll go ahead and fill those in for us. Now if we investigate these functions on the right-hand side, the right-hand output, again, we need to make sure that if we're putting in values to the right of 0, we need to use this part of the piecewise defined function. And if we look at the trend, we can see that we are clearly approaching 0. Like I'm losing decimal points every time I get closer and closer to 2. So we are approaching 0. We're trending towards 0. So that leads me to believe that the limit as x approaches 2 from the right of my function f of x is actually 0. And like I said in an earlier video, since the left-handed limit and the right-handed limit of this function are sending us to different places, if I were asked to evaluate the overall limit, or just this limit, approaching from both sides, we would say that this limit does not exist because the left-handed limit and the right-handed limit are two different values. We can also use these tables of values to recognize infinite limits. So this problem says evaluate each of the following limits. If possible, use a table of function values and graph f of x equals 1 over x to confirm your conclusion. Now this function is not defined as 0. Okay, we can't plug a 0 into this rational function because that will give us a 0 in the denominator, and we don't like that. So we're going to go ahead and use our method of plugging in values to the left and to the right of 0 to see what happens. Now I'll go ahead and fill out this table for us. So on the left-hand side, if I plug these values in, these negative values that are getting closer and closer to 0, we see something interesting happening. If I plug in negative 0.1, I get a negative 10. If I plug in negative 0.01, I get negative 100. What I really want you to notice is that as I take very small steps on this side of the function, so very small steps, this is not a very large step from 0.1 to 0.01. The output becomes very large. So what that tells me is that as I get closer and closer to 0, the output of my function is getting very, very, very large. This is unstable. We have, for every small step we put in, we have a very large output of the function. That leads me to believe that as I approach 0 from the left-hand side of this function, 1 over x, the limit is actually negative infinity. We're going off to infinity as we approach 0 from the left. Now let's take a look at the right-hand side. Go ahead and fill out, oops, these are actually supposed to be positives. Sorry about that. Go ahead and fill out the function's outputs on the right-hand side, and this function's we have a pretty nice symmetry, so we're going to get something very similar. Now again, as we take very small steps in our x values or inputs to our functions, we're going to get very, very large jumps in our output. So what that leads me to believe is that the limit as x approaches 0 from the right is actually going off to positive infinity on this side. And again, since our limits are sending us to two different places, we can safely say that the overall limit of 1 over x as x approaches 0 does not exist. The second part of this problem says to graph the function to confirm our conclusion, so I'll go ahead and do that for us. We can see this function does have a vertical asymptote. My graph isn't the best, it's not the most accurate, but you get the idea. We have a vertical asymptote right here when when x is equal to 0. We're never going to ever cross this line. We're going to get really close to it. We're never really going to cross it, no. And as you can see, we've sort of validated our results. If we look back at our table, we know that as we approach 0 from the left-hand side over here, our function values are just getting larger and larger and larger in magnitude. It means they're getting very large but negative. So we're kind of just going off to infinity, negative infinity in this direction. And likewise, if we approach 0 from the right-hand side, if we follow our curve from the right-hand side, our values are just getting larger and larger and larger. So we're approaching positive infinity on the right-hand side. This confirms what we saw in our table. That's all I have for you for this lecture. I look forward to seeing you all very soon.